All right, let's talk about section 3.1. Uh, in this chapter, it starts to really get into the big picture of what statistics is all about. Or when we say we're doing statistics, like what does that mean? So, what I thought would be helpful is to start off with just a picture of the big idea. So, whenever you're doing a study and you want to investigate or know something about a population, usually that population could be millions of people. And so for you to go and survey all of them, probably not a realistic idea to actually go and do that. Now, when someone is able to actually go out and collect data from every single person and calculate something like an average or a proportion, we call those parameters, right? So just think about like ACC, for example. ACC has more than 40,000 students. If somebody actually did go and measure their height then, of every single one of them, that'd be a parameter, right? That would be the actual average height for every single student. Or if you went and talked to every single one of them and found out what proportion of them are eating breakfast every morning, that would be a parameter. Now, since there's too many people often, and whenever you're doing your target population, like I want to go study them, there's just way too many people and it's just you on your lonesome. Plan B is to do just a sample and to let that sample give you a good idea of what might be true about the bigger population. So you might just do 50 people, you might do like 100 people. Now, whenever you use just a sample, it's not a parameter anymore. That's called a statistic. So a statistic is a value that you get calculated based on just a smaller portion of the population. And you let that statistic hopefully be, a best guess at what's true about the population. So some of your main key vocabulary words here are that whenever you do just a sample, it's giving you a point estimate. Or I think maybe even a simpler way to describe it is it's giving you like guesses about what might be true concerning the entire big population. So you're going to want to keep these two words together. Parameter, those are values related to the population. Numbers, values that represent the population. And then statistics are values or numbers that you calculate when you've only worked with just a smaller sample of the population. You'll also want to start keeping track of all the different notations that we use. So X bar is the notation for the mean from just a sample. Mu is the notation for a mean based off of the entire population. And then we've got P hat and P, which we introduced those at the beginning of chapter 2, are whenever you're doing a proportion from just a sample or the proportion from like every single person. And then we've got standard deviation and sigma are your notations for standard deviation, respectively, for sample and population. And then we've got correlation, which is the lowercase r and rho. Now, again, you're gonna be able to have a reference sheet while taking your test. So that would be somewhere on your reference sheet, a good idea to have just a little pocket of all the notations. Now, this example here is meant just to hash out this idea of, okay, are we dealing with a population or are we dealing with just a sample? And if so, that would be the indication that we're either doing a parameter or a statistic. So when you look at part A says that they were doing a study and they were trying to do the proportion, and it was based off all residents in a county who voted in the last election for mayor. So since they did it based off of all residents, that's a population, which would mean whatever they get from that study would be a parameter. And suppose they actually like really went and did it. Okay. Maybe it's a small county. And so then if it's population proportion or population parameter, then you would be using just a regular P for the notation. Now for B, B says that it was them doing the mean or an average of extracurricular activities, but when they did it, it was just based off of a smaller sample. So once they're done calculating that value, that would only be considered a statistic. And once they do have that value, they would use X bar because it was a mean from a sample. And look, that's where this helps right here. If it was a sample mean or mean from just a sample, that's a statistic, and you use X bar. Now maybe pause the video and try C on your own. Again, they'll give you what type of parameter it was or whether it was a statistic. They'll give you a clue as to whether it was a sample or whether it was a population. Okay, so we're looking for two different things here, whether this was the result of what they did, whether it would be a parameter or just a statistic. And this one, since they did it based off of all NBA players, and for us, that's it. That's the main trigger word for us whenever we're doing one of these homework problems is that if it says all, that's a population. And this would then be a parameter. And whenever they're done calculating whatever it is, which that thing was correlation, it would be right. Yeah, right there. Population, correlation, or a parameter based off the population. So it'd be rho. So you'll see some of these in the homework. And maybe I haven't, preached it enough, but just remember whenever you're doing your homeworks, there is an answer key that you should be leveraging before you submit your homework. This way, that way you can get immediate feedback, whether there's anything you need to fix or adjust. That way you can get, you know, hopefully all your points or hopefully only just like minor tiny deductions if you miss small little stuff. But um, cool. All right. Now, this here is, as I've been teaching this class over the years, is I learned that it's best to give students a template because I want you to look at the little prompt here. They're going to introduce a study, like what it was about, what they were trying to do, how they did it. But then they ask this question, and it says, give notation for the parameter and define the parameter within the context of the study's purpose. And I've often had students tell me that they're not sure what they're asking for there. And so what they're asking you to do there is just talk about what was the main, like the big goal of the study. Now, the big goal is that they wanted to know something about the entire population. So it's kind of going back to this picture here. All right. So what A is asking for is to describe like what were they hoping to accomplish? Like who was all the people who they wanted to study? What about all those people do they want to know? And then what B does is just look at, okay, what did they actually do with respect to a smaller sample? All right, so let's try this. Now, I've also learned that one of the best things I can do is give students a template. So in this little study here, it says that in 2012, they did a survey, and the survey was just based off of a sample of 2,253 US adults, and they found out that 1,329 of them reported using a search engine. So that many people said that they were on the internet every day. All right. Now, what we're going to do with this is whenever we talk about what the parameter was, like give notation, parameter, define the parameter, is you're going to use one of these two as a template. So since this one is not about means and averages, you don't need the top one. This was a study about proportions. They gave us what fraction of people were on the internet every day. So you're going to use this one here, which the notation would be P, because they didn't want to just only know about this sample of people. They used the sample people to hopefully give them a best guess about all people at this time period who were on the internet every day. And so when they say define the parameter, that's where you're going to use something like this, right? Just describe what the study was about. So it was to try to get the proportion. I'm probably going to write this out on 2 lines. Proportion of who? Of all, and this was about US adults. The proportion of all US adults who do or say believe what? In this case, who are on the internet every day. The proportion of all US adults who use a search engine every day. Now, again, that is meant to be sort of like the big goal. They wanted to know something about all people who do this internet thing like every day. Now, since they can't actually go out and survey every single US adult, plan B is, well, let's just do at least a sample. And that's where the 2,253 people come in. And that's what B wants you to talk about. B says give notation for the statistic. Remember, statistic means the sample. What did they find out from the sample? And so you would put P hat because statistics, samples, sample proportion, we use P hat. And then you would do your fraction. 13.29 out of 2,253 people said that yes, they're on the internet a lot. Then you would go to divide that to get your 0.59. So A, that's how you do A and B. A, use one of those two templates. B, just talk about what the sample said. So their guess at that time was about 59% of people are on the internet every day. Now, this is only a guess, so it could be off. Maybe back then it was really like 65%, or maybe it was really like 52%. Right. So, but again, hopefully this is a pretty good guess. And the reason why it might be a pretty good guess is that, they did over 2,000 people. That's pretty good. And then also it was random. So, pretty good chance that it probably wasn't biased. But again, it's still only a guess and it could be off. Now, the last little thing I want to mention in here is because it is only a guess, we've got to be honest and say, well, it could be off. So the only way that they could ever get it to be exact, like the perfect answer, would be right here. There's one little thing, is that you would need to yeah, what they would have to do if they wanted to get an exact value is they would need to go and survey every single person. That's usually what you'll see on some of these homework problems is like, if we wanted to get exact and it wasn't just a guess, you would have to go and ask or talk to every US adult. But again, that's going back to the big picture. Not everybody has the ability to go and do their entire population. So plan B is work off of just a sample of people. Now, I went ahead and did a second one here that now uses means. So it says they did a survey of a sample of US book readers. Again, they would have loved to talk to every single book reader, but time, resources can't do that. So they did just a sample of book readers and they found out that the mean number of books read last year was 17. So that's their statistic. Now, A's is just again same like the last problem, like give notation and define the parameter. In other words, like talk about what was their big ultimate goal. And since this one's about mean, you're going to use this one, right? They wanted to know the mean number of books read by all U.S. book readers. So you start off with mu, would be the population's average. You would start off with that this study was the type of parameter was a mean, and then you would talk about the variable, the mean number of books read by all U.S. book readers. And they also had in there the specific age, but right now I'm just mainly trying to focus on when you do the homework that you get like the main gist of it. Now, the things you need to make sure that you mention here is whether the study was trying to do a population or whether the study was trying to do a mean. Do not forget to put those two words in there. The other thing also is make sure that like, do you have to say all? You don't have to say all, but I think it's a safe word to use because again, don't put in here that they were trying to do the estimate or wanted to know something just about the people in the sample. No, this was their big goal was to know something about all of the US adults or all of the book readers. And then you would put the variable. The first one was about using the internet every day, then the next one was about how many books that they're reading, and then B, just like in this last one, what did the sample say? Well, for this B, it's the sample said that the average was 17 books based off of just a sample. So you would use X bar, it's a mean from a sample. And then like the last problem, this is only a guess. It could be off. Maybe it was really 20, maybe it was really 15. But if you wanted to get it exact, you would need to go and survey every book reader. And more specifically, we'll go ahead and put it in there, that we're 16 and older. I guess I should put 16 plus. Again, when you do the homework, definitely just like all other homeworks, come back to the lecture handout sort of as a template or a gist of like what you're expected to write in terms of the amount of detail for your responses. Now, the other big thing that we're going to do in this lecture is introduce sampling distributions. So a sampling distribution is going to be a dot plot, but each dot, what's going to be different is each dot is not going to be just one person. Each dot is going to be its own unique sample that's being pulled from the population. Now, the reason why it's a good time to introduce these is because now we're going to be talking about how samples are giving us best guesses for what might be true about a big giant population of millions of people. And the truth is that these samples are still only at best guesses, but some of them can be awful guesses, and some of them could be like really, really like good guesses in that when you compare them to the actual truth of the population, that they're not that far off. So here's what we're going to do. We're going to do an example here that first starts off with telling us what the truth is. So when you think about NFL football players who these are professional athletes, they get paid a lot of money. And whenever they did this a couple years ago in 2024, they got every single NFL player and they put into a data set how much they were all getting paid. And the average came out to be 3.6, like a little bit over $3.6 million. And this right here is the truth. This was the true mean or the true average. So no guessing. Like that is the actual solid hardcore truth. It was about 3.6 or a little bit over $3.6 million. Now, suppose we did not have access to all of the NFL players for that year, and we only had a sample, and we were going to have that sample be our best guess at what the truth might be. I want to show you how some of the guesses might be pretty good and how some of them might just be way off. So the way we're going to do this is with Stacky. And what Stacky can do is if it has access to the population, which it does, someone did put all the football players into Stacky, and you can say, hey, I want you to just grab me a sample, and you can even tell it like how big of a sample. And we're going to tell it just, hey, grab me like 10 players, just 10 random players. And we're going to use that to see if it gives us a pretty good guess at the average salary for football players. And keep in mind, it's really like 3.6 million, okay, or a little bit over 3.6 million. Now, we're going to do it not just once, we're going to do it, maybe a few times to get started, like 5 of them. And then we're going to go to do like 1,000 of these samples. But we're going to start with just doing one little sample to see, how good of a guess. And right here's the truth. 3.6 is the actual truth, but let's see how far off a sample or how close the sample is. So let's go here. Let's go to Stacky. I'm just going to do this from my iPad. And it's going to be, here's where we're going to go. Sampling mean, sampling distribution for a mean, NFL contracts, 4th edition, the year 2024. Let's go over here. Boop, boop. Go over to Stacky. Boop, 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 boop. And then once you get to Stacky, right here in kind of the middle of my screen where it says sampling distribution for a mean, go and click on that sampling distribution for a mean. And then you're going to go, this starts out with baseball players, and we need to switch it to the NFL players. You can see NFL contracts, 4th edition, and then they did a more recent one in 2024. And right there is where you can see the truth. It was 3.6 million was the actual like average for the players. Now up here is where you can see that it's already set to do samples of size 10. So what you're going to do is you're going to have Stacky and watch. Look right here. It says show data table. Yeah, it's got all the players. It's got like everybody, and it actually has them from highest to lowest. Hey, Dak Prescott. So if you're a Dallas Cowboys fan, you know who Dak Prescott is. But anyhow, you've got all these players and their salaries, and it's going to randomly pick 10 for you. And it's going to randomly pick 10 because right here we're saying randomly pick 10. And what I want you to do for this first one is you say you can generate a one, you can generate 10 samples or 100 or 1,000. I want you just to do one. All right, let's just do one right here. Boop, generate one. And so it randomly, there's my dot. Now your dot might be somewhere completely different. Mine right now is 4.254, which is that a bad guess? Yes, because the actual truth is 3.6. And this sample was guessing about 4.2. So it's a little too high of a guess. Now, over here, you can also see a quick little summary of your first little dot. You can even see if you click on the show data table, like which 10 random players it picked. And it won't pick the exact same 10 people as me. Again, it's random. So my first guess was on the high side, right? About a million, a little, what was that, like 3.6, like a little more than like about 0.6 of a million, like too high. But let's do a few more. I want you just to go here and I want you to click generate one sample 4 more times. So like in other words, do a total of 5. So one, let's see if I already done it. Yeah, I'm gonna just do it. Yeah, I did there. I'm gonna do it another one, and another one. At that point, I've got 5 samples, and there they are. Now, you can see from mine that I've got some that are guessing about a little under 2 million. You can see that I've got some that are doing about 4, 5, almost like 6 million. And so far, none of my 5 dots are actually like perfect guesses. Some of them are too high, some of them are too low. But then what I want you to notice is I've got a little arrow that's saying 3.561. Yours is going to say something different, but it's the average of my five guesses, although all five of them are actually incorrect. Average wise, they're not so bad. Yeah, average wise, like 3.56 is pretty close to the truth. And so the big moral of the story here is that when you are doing samples, the truth is some of them might be too low, some of them might be too high. So a good idea is to go ahead and do multiple samples so that if some of them are off, average wise, they actually together get pretty close to the truth. So 3.56. And here's what I want you to do. I want you to just come back here to the lecture handout and just try to put about where your dots were at. And again, it doesn't have to be perfect. I had a couple that were a little bit before two, and then I had some that were like kind of in the fours and the fives. And then the arrow for mine was like at 3.5 as like where the best guess was. And so a few little things that we want to just catch up on here for part A is, did any of your samples guess the truth? Did any of them get it exactly perfect? None of mine did. Most of mine were too low or too high. Now, if you got one of your dots to guess exactly 3.6, right? The 3.618, that's amazing. But probably for most of us, no, that's not going to happen. For most of us, some of the samples are going to be too low. Yes. Some of mine were too low. Some of them were too high. Yes. Some of them were too high. But the big moral of the story is go ahead and do more than one sample. Do two, do three, do four, do five. And because Stack Key has the ability to work really, really fast, let's just go ahead and have it do 1,000 of these. And so right there where it says generate 1,000, go ahead and click that. Boop. So now we got 1,005 of them. And you can see the graph there, and it's skewed to the right because not a lot of players are getting super high, ridiculous millions of dollars. I mean, most of them are still going to be uh, kind of at the central of the graph. And so right there is your after doing 1,005 of them, the average of all the samples is saying that the true average is probably about 3.656, which that's getting closer to the actual truth. Remember, it was just a little over 3.6. So if you got something on your side that's kind of around 3.6, then you're good. Like you've done your job. All right, so I'm going to go with 3.656. Go right back over here. 3.5. Wait, what was mine again? I already forgot. 656. 656. Now, it's also important for me to go ahead and say right now that this is definitely going to be one of the homeworks that might throw some of us off. Again, if we've gotten used to the routine of checking our answers with the answer key, and most of the time it's always been like, yep, same answer, same answer. But this one, there's going to be some variation. You will not get the exact same answer as I do because of the way that these are being created. It's through a random process of selection. Now your answer though should be similar. So as long as in your answer key, I've got 3.656 and you got 3 point like 6421 or whatever you got, you're fine. Now go ahead and just draw the basic shape of the distribution and note that yes, some of your guesses might have been ridiculously way off. Like some of mine were guessing that the average salary is like 12 million. No. Thankfully though, those did not happen very often. Most of them over here were kind of in the area of like the truth, like that 3 million mark. All right, let's try. Actually, we don't have too much left. So let's go ahead and let's start wrapping this up. So the main things I want to give you are sort of like the key takeaways to one of these distributions is that each dot is not just one football player. Each dot was like 10 football players, or each dot is one sample of. Now I'm going to leave this blank. In the last one, it was like each dot was like 10 random football players. And then each sample will be the same size. And things are being randomly generated. And if so, whenever you're done looking at one of these, and here's another one, these little dot plots or these sampling distributions, although some of the guesses are going to be too high and some of them are going to be too low, when you average out all the guesses, the center is going to be pretty close to the actual true population's parameter. So now for this example here, instead of doing, this was not about means, this one's about proportions. They were trying to do the proportion of people over 15 who have never been married. And they did this off of the census. So this was them pulling from the actual population of like everybody. And so they're trying to guess like what percentage of people that age, over that age, have not been married yet. And you can see that some of the guesses were saying like, oh, maybe like 26%, or some of them were saying like 38%. But like the football example, things way out in the far tells are not your best guesses. Your best guesses end up getting averaged into the middle. Now, one thing that you want to be really, really clear about these new graphs that we're looking at is like, what does one dot represent? And so whenever they ask you, what does one dot represent? There's two things that you want to say. That each dot, maybe I'll start this way. Each dot is a sample. Each dot is one sample. Then there's a second thing we're going to say, one sample of n equal to, they say it right here. These are all samples of size 500. So each dot is not just one person or one citizen. Each dot is 500 people. And each dot is giving you a guess at what the proportion might be. Like what might be the proportion of people who have not been married who are over that age. So again, like this dot right here, like for example, this one right here was guessing. I'll just pick on one of these right there. Like that was a dot of n equal to 500 people, and it was guessing about 36% have not been married. Now, again, the ones that are on the tail that are happening not as often are not your best guesses. You're going to go with the average of them. So 0.32, you always use the center. The center is the one that's going to give us probably our most close to the true proportion. So about maybe 32%. And again, why do we use P without the hat? For this one, we were specifically trying to do the population. And for those, we use P without hat. Now, suppose we were to take another sample, like do one more, and how likely are we to get something like 25%, 30%, 37, and 74%? So here's what I want you to do with this. I want you to come here and do like our what we would do in the past, our 95% interval. Maybe something like that. And we're going to slice this into anything in the middle that seem to happen a lot more often. These are the ones that we'll categorize as being more likely to happen. But anything on the tails that seem more like rare or less frequent, They might happen, but they're not something that you would bet on. Then anything that's like way out here, these are very unlikely, like not going to happen. And so for us to maybe do another sample and think about the likelihood of us getting like 0.25, that's like in this little zone of like, I mean, it might happen. It's not completely off the grid. And so that would be they use these little either I or double I or triple I. This would be an II. And then something like 30%, that is right there. So it has happened quite a few times. So that one's got a really good chance of maybe being likely to occur. So that would be an I, like pretty good chance, reasonably likely to happen. 0.37, that's like out here somewhere on the tail. So it could happen. Like, I mean, they saw a few like 0.36 and 0.38, but I mean, probably not the best bet, but it could happen. And then 0.74 is like way out here in like no man's land. Yeah, it only went as far as like 38, maybe 39. So 0.74, that's going to go with I. Like unlikely, nope. Don't bet your firstborn child on that. All right, so let's go to start kind of winding this down. There's not a whole lot left, but when we see what's going to start showing up more and more is this idea of standard error. So standard error is a new way of describing deviation. Standard deviation, when we first saw that, was whenever you had one sample, how different were the values within that one sample. But now that we have multiple samples, that's all that we're doing. We're just switching it to standard error. And that is talking about how different or similar the samples are in terms of their values. Like, are they spread out? Are they more narrow together? So a smaller standard error would mean that things are more packed together. Like you'd have a more skinny graph. And the reason why that's considered a good thing is because whenever all the values are guessing all kind of about the same number, then we have a smaller window for where we think the actual population parameter is. And so I've always used this sort of as a, well, what do you mean that a smaller standard error where things are more packed together gives you more confidence? So let's suppose that somebody was to put an apple on your head, and you have two archers. Let's call them like Archer A and Archer B, who are going to be, you're going to get to choose who's going to shoot the arrow off your head. But you get to see a sample of their work. In sample A or Archer A, like he hits right here, boom. He hits right there, boom, boom, boom. I mean, he's no Hawkeye, but he's still pretty good. And then Archer B, boom, hits right there in the middle. And then they also hit over here, and they hit over here, and they hit over there, and they hit over there. All right. That's my illustration of standard error. Like, who would you have more confidence in being able to maybe get and you have to pick either A or B. Your life depends on it. Unless you're living life on the edge, you would pick B. But no, if you want to live to see another day, A has a smaller standard error. Like more of the shots are together, and so it's giving you a better estimate of what they're likely to be able to do. Now, one of the things that we'll talk more and more throughout the semester is that anytime that you use larger sample sizes, or as you increase your sample size, right? your graph is going to shrink down, or your standard error is going to get smaller and smaller. I thought the best way is just to go and show you. Like this one right here has a very, very like narrow graph. And the reason why that one would be so narrow is because if they used either 20 or 100 or 400 dots in each sample, it would be the 400 one, right? Where each one of these dots is like 400 cases inside of each dot. That's the way to shrink your standard error. So you get a really skinny graph and a really narrow set of like estimates. Now, something that's really wide like that's all over the place, would be probably because they didn't use very good sample sizes. Maybe only like wimpy, like 25 people per dot. And then the one that's so, that's not too wide, not too narrow, it's just kind of right in the middle, would be if they use like the medium size. But the main thing that I want to stress here is that graph C is the one that is most narrow and would also be the one that has the smallest standard error. So it's like Archer A, where more of the dots were like hitting close to like the bullseye. And again, the way that you can achieve that is by using samples that are a lot bigger. And then I'm going to finish one last little thing here. And forgive me if I have a student who shows up right now for office hours. Like I'm about to run into office hours. And so if they show up, then I'll ask them to give me just a couple minutes to finish this. But here we go. I want to do one where it's about proportions, where again, the big thing today is that when you do a sample, it's only giving you a best guess, and it might be off, it might be too low, too high, but increasing your sample size is a good way to help get your estimates to be a lot closer to the truth. In this example, we're going to use this. It's a sampling distribution for a proportion. It's about Hollywood movies and what proportion of them were comedy. And someone actually went and did it. They did it to where they got all the movies, and it was for a particular year. I can't remember what year it was, but for one particular year when they did it, they found out exactly this is the truth. This is the true value of comedies, that 11.6% of them were dedicated to comedy. Now, what I want to do mainly in this last example here is to show you that what if we were to do samples of size 10 versus samples of size 50? What would it do to the shape of the graph? What would it do to our estimate at the center? And then what would it do to our standard error? And the main thing I want to show you is that the standard error is going to get smaller if you do bigger sample sizes. So let's go over to stat key, and we're going to go to the, earlier we did sampling distribution mean, but now in the homework there's going to be one where you're going to need proportion. And you're going to go to the drop down, you're going to find the Hollywood movies, and there is a fourth edition and a third edition. Make sure that we're doing fourth edition comedy. And you can see right there is what they found out, that 11.6% of all the movies for that particular year were comedy. And right now we're going to go with, I think I said size 10. Let me check real quick. We want to start off with first just samples of size 10. I'm pretty sure that's what it was. Whoa, where's my thing going? Hopping all over the place. There it is. Yeah, we're going to start off with just size 10. So let's go ahead and change it to wimpy size 10. You're going to click right here. You're going to do 10. You're going to hit OK. And now you don't have to do one at a time. You can go ahead and say, hey, I want you to get 1,000 samples. And what I want you to notice is that some of the samples we're guessing like 40%. Some of them might even, we're guessing like 50% of them are comedies. But right there where you see my arrow, you should also see an arrow for yours as well. The average of all of these guesses was 0.119, which is not bad, right? The average of all the guesses came out to be pretty good, 0.119. And then the standard error is zero point 0.1. And so I want you to go ahead and put, that the graph is skewed to the right. And then we've got 0.119. And I'm going to write these down for myself as well, because once I skip over them, let's see if I'll be able to remember them. 0.119 and 0.100. Now yours are going to be similar to mine. Might be the same, but might be a little bit different. The shape is skewed right. And then I got for my center, which is the average of all the guesses, and then 0.100. Now we're going to repeat this again to see what happens to the shape whenever we do larger sample sizes, let's say 50. What do we get for our estimate in the center, and then what happens to our standard error? And it should be, here, I'm going to spoil it. It should be that the standard error decreases whenever you increase the sample size. But let's try. So keep in mind for this homework, there's going to be maybe for one homework problem, two of these graphs where you have to show like the smaller sample size and the bigger sample size. Let's go ahead and just reset the plot, just clear it. And let's not forget to change the sample size to 50 now, which would be more stronger. And then once you've changed it to 50, go ahead and generate 1,000. Look, now we've got symmetrical bell shaped. You can also look right there in the middle. I've got a guess of 0.118. So although some of them are guessing like none of them are comedy, or, 30, 25%, 26% were comedy, the average of all the guesses is 0.118. You can also see that here, which is not a bad guess. Remember, the truth was 0.116. And then now we also have a smaller standard error. So I'm going to write these down. I've got 0.118 as the average of the guesses, but my standard error is also smaller, 0.044. Again, the main thing that I want to stress here is that the big thing is that whenever you do larger sample sizes, it will help you get smaller intervals, or better estimates, a tighter window of estimates. Symmetrical, bell shaped, 0.118, and then 0.044. All right, but that is a good chunk of stuff that we did in this lecture. I'm going to go ahead and stop the recording there. Of course, if questions come up, don't hesitate to reach out. But I will see you on the next video.